Welcome students to the 16th lecture of the MOOCs course on fuzzy sets, arithmetic and logic. In the last class, we have studied the extension principle, which allows us to extend the notion of a function from crisp sets to the domain of fuzzy sets. Today, in this class, we shall look at extension principle and arithmetic. With respect to fuzzy sets. Earlier we have done fuzzy arithmetic, and if you remember, we have used alpha cuts for fuzzy arithmetic, namely say plus, minus, multiplication and division. If you remember, we have done them. We have used interval arithmetic on alpha cut of A and alpha cut of B, and we have used that alpha cut of A of B is equal to alpha cut of A of alpha cut of B, where O stands for any one of the operators or any of the operators plus, minus, star and division. But we are not sure that actually the set obtained by arithmetic operations yield continuous fuzzy numbers. We have sort of assumed that result, that when we are operating between two alpha cuts, and that will indeed generate the alpha cut of the final result. So, the following theorem establishes that fact where we have used extension principle. And A and B are continuous fuzzy numbers. Then A O B is a continuous fuzzy number that is for all alpha belonging to 0 1, alpha cutoff A of B is a closed interval and A of B is continuous. If we show that, then we justify why you have used the interval operations on different alpha curves to get the final result. So, let me illustrate how we define the operations addition, subtraction, multiplication and division using extension principle. So, mu A plus B of Z is equal to supremum over all those x belonging to A and y belonging to B such that x plus y is equal to Z minimum of mu A of x and mu B of y. In a similar way, mu A minus B of Z is equal to supremum over x comma y such that x minus y is equal to Z. Obviously, x belongs to A, y belongs to B and minimum of mu A x comma mu B y. In a similar way, mu A star B of Z is equal to supremum over x comma y such that x star y is equal to Z and minimum over mu A x and mu B y, and similarly mu A slash B of Z is equal to supremum over x belonging to A and y belonging to B such that x by y is equal to Z minimum of mu A of y and mu A of x and mu B of y. Before going further, here is an illustration. Let A equal to TFN minus 1, 1, 3 and B is equal to TFN 1, 3 and 5. Therefore, alpha cut of A is equal to minus 1 plus 2 alpha and 3 minus 2 alpha, and alpha cut of B is equal to 1 plus 2 alpha and 5 minus 2 alpha. Therefore, by interval operation, alpha cut of A plus B of Z is equal to, we can get by adding them, is equal to 4 alpha comma 8 minus 4 alpha. And we have already seen that A plus B is also going to be a triangular fuzzy number, and that is going to be 0, 4 and 8. Therefore, mu A plus B of Z is equal to 0 if Z less than 0 or Z greater than 8. Between 0 to 4, it is going to be Z by 4, and between 4 to 8, it is going to be 8 minus Z by 4. So, when Z is equal to 8, it is 0. When Z is equal to 4, it is 1. Therefore, mu A plus B of 2 is equal to 2 is in this range, and therefore, it is going to be 2 by 4 is equal to half. Now, we need to check if by using this formula whether we can get the mu of 2 is equal to half or not. So, let us do that. Note that there are infinitely many combinations that make x plus y is equal to 2. So, let us first draw the two A is from minus 1, 1, 3. Therefore, it looks like this is the membership for A. Similarly, membership of B, B is from 1 to 3 and 5. So, B will look like something like this. Sorry for the drawing, but these are triangular fuzzy numbers. Now, let us look at in how many ways we can get A plus B is equal to 2. When x is equal to minus 1, y is equal to 3, it is one possibility. Another possibility is, say, x is equal to 1, y is equal to 1. Let me consider another possibility, x is equal to 0 and y is equal to 2. So, let us see intuitively what is happening. When x is minus 1 and y is 3, then membership value for x is 0 and mu b of 3 is equal to 1. Therefore, minimum is equal to 0. Mu a of 1 is equal to 1 and mu b of 1 is equal to 0. Therefore, minimum is equal to 0. Now, let us move. Suppose I increase the value of x from minus 1. Therefore, the value of b has to be appropriately reduced from 3 and possibility that these two when add up will give me 2. Similarly, as we go up and as we go down with this line, we find that at this point both of them attain the value half. Therefore, what is this point? This is 0 and what is this point? It is 2. Therefore, mu a of 0 is equal to half, mu b of 2 is equal to half, and if we go above this, this will fall below half, and if we take a point above this, then here the mu falls below half. So, in all the cases the minimum will be less than half, but when x is equal to 0 and y is equal to 2, the minimum is half. Therefore, we can see the maximum possible value, or say therefore, the supremum over x belonging to A and y belonging to B such that x plus y is equal to 2 is minimum of mu A of x, mu b of y, and that value is coming out to be minimum of half and half is equal to half. Therefore, mu a plus b of 2 is equal to half. And in any case, we have already seen this result some time earlier, but here we show that with the help of extension principle we obtain the same value. I request you to try for other values in a similar way. Okay. So, with that background, now let me prove the theorem. We want to prove that A of B is a continuous fuzzy number that means alpha cut of A of B is a closed interval for all alpha, and second thing we need to prove that A of B is continuous. So, let us first prove that alpha cut of A of B is closed interval. For all alpha belonging to 0, 1. For that, we show that alpha cut of A of alpha cut of B is equal to alpha cut of A of B, and therefore, since alpha cut of A and alpha cut of B are closed interval, therefore, alpha cut of A of B will also be a closed interval. And why do we say that these are closed interval? Because it is already given that they are fuzzy numbers, and we are doing interval arithmetic on that, and we want to show that this is also going to be a closed interval. So, let Z belongs to alpha cut of A of alpha cut of B implies there exists x naught belonging to alpha cut of A and y naught belonging to alpha cut of B, such that x naught of y naught is equal to z. Therefore, mu A of B of z, which is equal to supremum over x y such that x of y is equal to z, minimum of mu A of x and mu B of y, which is greater than equal to minimum of mu A of x naught and mu B of y naught. That is obvious, because x naught y naught produce z, and I am looking at supremum of all such x y. Therefore, for a particular case it has to be less than equal to the supremum, and we know that both of them have membership value greater than equal to alpha, because they belong to the respective alpha cuts. Therefore, minimum has to be greater than equal to alpha. Therefore, this is greater than equal to alpha, which implies that z belongs to alpha cut of A of B. Therefore, we started with a z which belongs to alpha cut of A of alpha cut of B, and we find that z belongs to alpha cut of A of B. Therefore, we say that alpha cut of A of alpha cut of B is contained in alpha cut of A of B. So, this is one way of the proof. Now, we want to prove that If Z belongs to alpha cutoff A of B, then Z belongs to alpha cutoff A of alpha cutoff B. This proof is slightly tricky mathematically and it needs some knowledge of analysis. So, try to understand it carefully. Since Z belongs to alpha cutoff A of B implies supremum over x comma y such that x of y is equal to z, minimum of mu a x comma mu b y is greater than equal to alpha. That means that if we consider any alpha prime which is strictly less than alpha, then we will get x prime and y prime such that x prime of y prime is equal to z and minimum of mu a of x prime and mu b of y prime is greater than alpha prime. Because if we do not get such x prime and y prime, then obviously the supremum of the minimum cannot be alpha, which is strictly greater than alpha prime. Therefore, the moment we choose any alpha prime which is less than alpha, we will get x prime y prime, which will produce the same z under the operation, but the minimum of this has to be greater than alpha prime. Therefore, given any epsilon greater than 0, we choose a sequence of such alpha prime such that alpha prime converges to alpha, and for each such alpha prime we identify x prime y prime such that x prime of y prime is equal to alpha. How do you do that? We do in the following way. Given alpha, we define n is equal to 1 by alpha floor of that plus 1, where is equal to the highest integer, that is less than 1 upon alpha. Now, we construct alpha n prime, the sequence of that as follows. Alpha n prime is equal to 1 minus 1 upon n, so alpha minus 1 upon n, where n is greater than equal to capital N. Therefore, as explained above, we shall get sequence x n y n, n goes to infinity, such that x n of y n is equal to z. Since all alpha cuts are closed intervals, therefore, both x n and y n sequences are bounded sequence. Because we are taking numbers from within the alpha cut, and since these are infinite sequence, therefore, both x n and y n will have at least one point of convergence. Say x naught is a point of convergence of x n. What does it mean? It implies that there exist infinitely many xi's such that mod of x naught minus xi is less than epsilon for any epsilon greater than 0. Let x n I be the subsequence of x n such that x n I converges to x naught. Now, let us look at the corresponding subsequence, namely y n I of y n. So, first we have chosen a subsequence which is converging to x naught. Then we are only looking at those indices of that subsequence, and we are looking at corresponding y values. Since y n I is also a bounded sequence, it has a point of convergence say call it y naught, and let y n I j be the subsequence of y n I such that y n I j converges to y naught as j goes to infinity. Now, let us focus on x n I j and y n I j, and therefore, x n I j is converging to x naught, y n I j is converging to y naught, and x n I j of y n I j is equal to z for all j. Now, since O is a continuous function, z is equal to limit j going to infinity x n I j of y n I j is equal to limit j going to infinity x n I j of limit j going to infinity y n I j is equal to x naught of y naught. Now, mu a of x n I j is equal to alpha minus 1 upon n I j, and mu b of y n I j is equal to alpha minus 1 upon n I j. Therefore, mu a of x naught is equal to mu a of limit j going to infinity of x n I j is equal to limit j going to infinity mu a of x n I j is equal to limit j going to infinity of alpha minus 1 upon n I j is equal to alpha. Greater than equal to alpha. Similarly, mu b of y naught is also greater than equal to alpha. Therefore, we find there exists x naught belonging to alpha cut of A and this implies that y naught belonging to alpha cut of B. Therefore, we get x naught belonging to alpha cut of A and y naught belonging to alpha cut of B such that z is equal to x naught of y naught. Therefore, z belongs to alpha cut of A of alpha cut of B. Therefore, we started with Z belonging to alpha cut of A of B, and we find that Z belongs to alpha cut of A of alpha cut of B. Therefore, alpha cut of A of B is contained in alpha cut of A of alpha cut of B. Earlier, we have shown alpha cut of A of alpha cut of B is contained in alpha cut of A of B. So, together we prove that alpha cut of A of B is equal to alpha cut of A of alpha cut of B, and therefore, alpha cut of A of B is a closed interval. So, let me repeat, our aim is to show that alpha of B, where of means any of the operations addition, subtraction, multiplication or division is a continuous fuzzy number. We started with that proof, and we said that it can be proved, that we want to prove that A of B is a closed interval, and for all alpha. In our proof, we did not choose any particular alpha, and therefore, since it is true for all alpha, therefore, alpha cut of A of B is a closed interval for all alpha. Now, what remains to be proved is that A of B is continuous. Suppose A of B is not continuous. And let Z naught be the point of discontinuity. Now, we know that for a fuzzy number, the membership function Lx and Rx are right continuous and left continuous respectively. If you remember, quite a few classes back, when we were discussing the membership of a fuzzy number, we have these characteristics. So, let us look at the membership function. So, suppose this is the Lz, and suppose this is a point of discontinuity. Therefore, as we come from this side, we will come close to this point, but there is going to be a gap between them or a jump between them, because this is a point of discontinuity. So, without loss of generality, let Z naught be on this left side. If it is on right side, this is the similar situation. If it is a point of discontinuity, we will get a very similar structure here. In either case, it will be the same. So, when we prove for Lz, it will also hold good on this side. Since Lz is right continuous, we have limit z going to z naught minus of mu a of b of z is less than mu a of b of z naught. As we can understand, there is a gap, therefore, membership has to be strictly less than mu n of b of z naught, which is equal to supremum over x y equal to z naught minimum of mu a of x comma mu b of y. Let x naught and y naught be such that z naught is equal to x naught of y naught. Therefore, limit z goes to z naught minus of mu a of b of z, it strictly less than minimum of mu a x naught and mu b y naught. So, we establish one inequality, let us call it A. Now, let us consider a sequence Zn such that Zn less than Z naught for all n. Let xn and yn be sequences of x and y such that xn of yn is equal to Zn, and xn converges to x naught and yn converges to y naught. Since the operations are continuous, therefore, limit z goes to z naught minus of mu a of b of z is equal to limit Zn going from z naught minus, because we have chosen all Zn to be less than z. So, they are coming from left side of mu a of b of z is equal to limit n going to infinity mu a of b of Zn is equal to lim n goes to infinity supremum of Zn equal to x star y, all those x y which lead to Zn, minimum of mu a of x comma mu b of y. Note that we have chosen one particular x n y n, but it is not mandatory that that is the only pair that will produce Zn. There may be many such x y pair which can produce this Zn, which is greater than equal to limit n going to infinity of minimum of mu a of x n and mu b of y n. This is because this is the supremum and x n y n are only a particular choice. The supremum has to be greater than this, is equal to minimum of limit n going to infinity mu a of x n and limit n going to infinity mu b of y n is equal to minimum of mu a of x 0 comma mu b of y 0. Therefore, we find that limit z going to z naught minus mu a of b of z is greater than equal to minimum of a of mu a of x naught comma mu b of y naught. Earlier, if you see, we have shown that limit z goes to z naught minus mu a of b of z is less than minimum of mu a x naught and mu b y naught, and now we have identified that this is the inequality is reversed, it is greater than equal to this. Therefore, there is a contradiction. This contradiction came because we assumed that there exists a point of discontinuity at z naught. Therefore, what we prove that there cannot be any point of discontinuity in a of b. Therefore, that is a continuous function. Since we have already found that all intervals are closed intervals, and here we find that a of b is a continuous. Therefore, we conclude that a of b is a continuous fuzzy number, and therefore, that allows us to work on the alpha cut of a and alpha cut of b to generate the alpha cut of a of b, where of is any of addition, subtraction, multiplication and division. Okay, friends, I stop here today. In the next class, I shall do some more arithmetic, particularly in solving certain fuzzy equations. Thank you.